Generic text fine-tuning often yields suboptimal results for instruction-following models. Llama 3 requires structured input for optimal performance alignment. Custom JSON datasets must strictly adhere to the Llama 3 instruction format. This structure involves nested dictionaries defining roles: system, user, and assistant. Incorrect formatting causes catastrophic forgetting or poor instruction adherence. We utilize the Hugging Face datasets map function immediately. This enforces the exact conversational flow required by the model. This preparation step is the most critical for successful adaptation. The dataset must be an array of objects for the SFTTrainer. Each object contains a single key named messages. The value of messages is an array of individual message dictionaries. A message dictionary requires two keys, role and content. The system role defines the overall context or the model's persona. The user role provides the specific input prompt or query. The assistant role provides the desired output response. This specific structure is non-negotiable for effective supervised fine-tuning. Ensure every conversation starts with a system message for best results. Fine-tuning Llama 3 8B demands efficient memory management on standard GPUs. We utilize 4-bit quantization via the Bits and Bytes library. Install the latest versions of transformers, accelerate, and PEFT for compatibility. Load the Llama 3 8B Instruct model directly using bfloat16 precision. We apply NF4 quantization during model loading. This reduces memory footprint significantly while maintaining acceptable performance. A minimum 24GB GPU is recommended for practical batch sizes during training. We define the LoRA configuration using PEFT config from the PEFT library. Set the LoRA rank, R, typically to 16 or 32 for robust learning. Alpha should be double the rank for proper scaling of the weights. Crucially, we must target the attention projection layer specifically. These layers are named Q_proj, K_proj, and V_proj in the Llama architecture. Targeting these layers ensures efficient adaptation of the attention mechanism. Set bias to none and task type to causal language modeling. The Llama 3 tokenizer includes specific control tokens for conversation boundaries. We apply the tokenizer's built-in chat template to the structured JSON data. This converts the messages array into a single, correctly formatted prompt string. Set padding to true and truncation to handle varying input lengths efficiently. We must ensure the model does not learn to predict the input tokens. Set labels to -100 for all tokens belonging to the system and user roles. Only the assistant response tokens should contribute to the loss calculation. Instantiate the SFTTrainer from the TRL library for streamlined training. Define the necessary training arguments for optimization. Set the learning rate typically between 1e⁻5 and 5e⁻5. Use a cosine schedule with a warm-up ratio of 0.03 for stable convergence. Gradient accumulation steps reduce memory pressure while maintaining an effective batch size. Set logging steps frequently, perhaps every 10 steps, to monitor convergence immediately. Use one epoch initially to gauge the required training time and loss reduction. Start the training process using the trainer.train method. Monitor the training loss curve closely for immediate feedback. A rapidly decreasing loss indicates successful adaptation to the custom data structure. If the loss plateaus quickly, the learning rate might be too high or the dataset too small. Save checkpoints periodically to prevent data loss during long training runs. Integrate weights and biases for detailed visualization of metrics. Early stopping based on validation loss prevents overfitting to the specific JSON examples. LoRA weights are separate from the base model during the training phase. For production deployment, merge these adapters back into the base model weights. Use the model.merge and unload method after training completion. This creates a single, deployable model file without external dependencies. Save the merged model and the updated tokenizer to disk using the save pre-train function. This final model is ready for inference without requiring the PEFT libraries or quantization setup. Load the merged model using standard auto model for causal LM for testing. Test the model with new JSON inputs that follow the exact instruction format used during training. Validate that the model generates responses adhering to the desired structure and content. Successful fine-tuning results in highly specific, context-aware outputs. This demonstrates true domain adaptation beyond the base model's general knowledge. Always test edge cases defined in your custom JSON dataset.